Assalamualaikum warahmatullah. We are now in part 2 of force method for indeterminate structure. And recall from the last part of the video, what we were doing is we define the concept of force method where we have an actual structure, and using method of superposition, we divide the structure into two categories, which are primary structure and redundant structure, and the addition of these two structure should get us back the actual structure. Okay, and then we also developed a compatibility equation as shown here, and finally we find a relationship for support reaction at B, which is negative delta B naught divided by delta BB. So now we are going to continue to use virtual work method in order to find the displacement, and then plug in into the support reaction at B in order to find one of the unknown. So let's see. To find first delta B naught here, okay. Notice that in order to find, okay, let me draw the displacement at B first. Okay, due to the primary system, we want to find what's the displacement delta B naught. Okay, so what we are going to do is we are going to use our principal virtual work method. Okay, so in order to find delta B naught, what we need is another system, which is our virtual system, removing the load and applying a unit load at the point where we want to find the displacement. Okay, and the value is 1. So this is our system, and this is our virtual system. And then if you can recall, delta B naught would be what? The integration from 0 to L, capital M, which is the internal moment due to the actual load, small m, the moment due to virtual load, divided by EI dx. And if you actually look at this system, okay, you will notice that the virtual work system for our primary structure is actually our redundant system. So these two systems are the same. So it makes our life a lot easier now, because we need to just resolve for our redundant system to get our displacement for primary structure. Okay, how about the displacement due to the redundant system? So let's again draw here. For our redundant system, we have a unit load here, and then we need to find d small delta BB. So virtual principle says that if we want to find the displacement at B, what we need to do is remove the load and then apply a unit load at point B. Okay, so as you can see, for to find small delta BB, our virtual work system is the same as our actual system. So if we write down small delta BB, it's just going to be what? 0 to L, the limit, and then it's going to be small m, okay, the actual system, multiplied by the internal moment due to virtual system, which is again small m, divided by EI dx. Now it is just the same moment that we are considering twice. So now this simplify our problem a lot. So, okay, so first let us proceed with finding capital M and small m. So for our virtual, this is for our actual system. Okay, we have a load here, 50 kilonewton per meter, and we also have our redundant system, which is a unit load. Okay, in order to find the internal moment due to this load, the easiest way is to cut the section from the right, because you don't need to find the support reaction here. Okay, you can just straight away analyze. So if you cut the system here, okay, you must do the same for your redundant system. Okay, cut it here, and then let's take this distance as x. Okay, and then draw the free body diagram at the cut. So for the actual system, your free body diagram will look something like this. Remember, your internal shear and internal moment is positive this direction. This is capital M, the moment due to actual system. This is x, and the unit load is 50 kN per meter UDL. For our redundant system, again, okay, this is 1. The distance would be x, and then you have internal shear and moment, and this would be our small m. Okay, so our internal moment, capital M, would be negative because it's the same direction as our moment, 50 x squared divided by 2. And for our small m, which is internal moment due to the virtual load or redundant system, it is going to be 1 the load times the distance x. Okay, now let's proceed with finding the displacement. Okay, I would highly suggest you to make it in tabular format, means make it in a nice table, because right now this might seem not important, but as your structure becomes more complicated, then you can easily observe the difference in moments using table. So let's make a table. So the first, let's make a table. So the first column would be our member. So if you can still remember, let me just redraw the member. Your member was like this. This is point A, this is point B, and the length is 10 meters. Okay, so the member that we are talking about is member AB. Okay, the next column is the origin. So the cut that we make originates from B. Originates from B, so this is actually point B. So your origin is B. Our limit for the integration is from 0 to 10. Okay, 0 to 10. So the capital M would be negative 25x squared, while our small m is 1x. So now you can easily solve for the displacement. So delta capital B naught is simply the integration from 0 to L capital M small m over EI dx. Okay, and basically this would be the integration from 0 to 10. Okay, and then you have capital M is negative 25x squared, small m is x divided by EI dx. Okay, now if you try to solve for this, you will get 1 over EI, you can take it out, it's constant. It will be negative 25x, this is x cubed, so it's going to be x to the 4th divided by 4, and the limit is 10 to 0. Solve this using calculator, then you will find that the value is negative 62,500 divided by EI. Okay, and then the next is to find the small delta BB. So small delta BB is again 0 to L small m multiplied by small m divided by EI dx. Okay, so we can take 1 over EI out. Then the limit will become from 0 to 10. Small m is x multiplied by another x dx. And if you solve this, you will get so x cubed divided by 3 EI, where the limit is 0 to 10. So you will get 1000 over 3 EI. And finally, we are going to solve our um, compatibility equation. Okay, if you still recall, we have write down our equation for RB. RB was negative of delta B naught divided by delta BB. Okay, and it will be negative of delta B naught, so negative 62,500 divided by EI, and delta BB is 1000 divided by 3 EI. Solving this, you will get the value of 187.5 kilonewton, and it is positive. Okay, this is our reaction at B. So let us just scroll up to the original diagram and see what is RB just now. Okay, just scroll up. Okay, so based on our redundant, RB is okay, so let me just divert your attention. So if you look at the redundant system, look at my arrow here. Okay, RB is a unit load that you put upwards. Okay, so when you did the calculation, you find that RB was positive, so it simply means that RB is actually a positive force pointing upwards with a value that you calculated just now, 187.5 kilonewton. Okay, once you get RB, now your number of unknown from 4 unknowns has reduced to only 3 unknowns, and the unknowns are, if you look back at actual equation, it's AX, AY, and bending moment. And because you have 3 equilibrium equation, you can then solve for the remaining 3 unknown. Okay, it can only be done once you find one of the unknowns. Okay, with that, I hope you can try out and find the support reaction at A, and then also draw the shear force and bending moment diagram. And that's about everything about force method that you need to know, and this is only for beams and frames. We will try a few examples and then proceed with virtual method for trusses. Thank you very much.